This conference will now be recorded.
Very good evening, students. Yesterday we had discussed application of Savart's law for a circular current loop. Okay. So this application we had already seen yesterday. I'll just recap a bit. Okay. So magnetic field due to a circular loop. So what we have seen that the magnetic field created by a circular loop will be always along the axis of the loop. And if we calculate the magnetic field at any point on the axis, suppose this is a point P at a distance x. So what was the expression we have found out? That will be obviously in this case x-axis. So Bx is equal to mu0 I by 4 pi. Sorry, this is not 4 pi, mu0 I by 2. So this will be here, this is r square divided by 2 into x square plus r square whole to the power 3 by 2, where capital R is the radius of the coil or loop, small x, so this x is the distance from the center of the loop. It is the distance of the axial point from the loop. Okay, so this is the main formula which you get for axial magnetic field produced by a circular loop. Now this has few special cases we have seen. Suppose case 1, if like magnetic field at the center, magnetic field at center of the loop. Okay, center of the loop. How do we find out that? See, put x is equal to 0. So that means this is here. So put x is equal to 0. So after putting x is equal to 0, what we get? B at the center, BO, let us write B at O. So mu0 I, this is r square, divided by 2 into this x is 0, so this will be r cube. That means you get mu0 I by 2r. Okay, so magnetic field at the center will be this one. We can just keep this. Okay, so this is the thing. Now there is another case 2, say. So what is this case 2? When this axial point is far away, okay, it's far away, that and such that x is much greater than the radius of the loop itself. In that case, see, in this formula, in this expression, we can neglect the r square. So in that case, what will happen? Bx will be mu0 I r square divided by 2. See, r can be neglected here, right? So this will be x cube. Okay. So mu0 I r square divided by 2x cube. Okay. So what is that? The field is directed along the x-axis in this case of the loop, and it is falling off. Magnetic field is falling off. See, magnetic field Bx is falling off cubed root, like it is inversely proportional to this cubed root of the distance or x. Okay, so this is second case. Then let us see third case, case 3. So case 3 is that suppose we need to find out magnetic field on the axial point, which is exactly equal to r. X is equal to r. That means radius and the axial point, distance of the axial point from the center of the loop is same. In that case, how do you get here? See, Bx will be mu 0 I. Let us take this as r square itself. Let us take this as r square, and x also let us take as r square. Then see, we will get 2 r square whole to the power 3 by 2. Okay, so this would give you mu 0 I, r square gets cancelled. This will be 2 by 5, so 2 to the power 5 by 2, and this will be r cube, this r square, so this is r. Mu 0 I by 2 to the power 5 by 2 r. Okay, r is the radius of the loop. So this is the formula. So these are the formula related to the circular loop. Now, as you can see from the general formula, that mu 0 I by 2, this is here r square divided by x square plus r square whole to the power 3 by 2. So in this case, see, at the middle or the center, at the center of the coil, the magnetic field will be maximum. You can see that here. This is a magnetic field at the center. So that will be maximum. And on either side, if you go on either side, x is positive, negative. So on either side of that, you go, you get smaller and smaller value. And since the variation of magnetic field, the variation of magnetic field of a circular coil with distance from the center Okay, so if we, in this case, x-axis, right? In our case, the magnetic field is developed on the x-axis of the loop. And see, if we go from, like, if I'm here at this particular position when the distance between them is very, very, like, the axial point is just coinciding with the center of the loop. So in this case, like, see, at the center, magnetic field is maximum, and that's how it is this. And as you put this value of x again and again, it will actually decrease the value of magnetic field on either side. If you take minus x and plus x, both sides, it will actually decrease the magnetic field. So it is kind of a bell-shaped curve. Okay, bell-shaped curve, bell-shaped curve, and easy to remember. Okay. Bell-shaped curve. On either side of the peak value, on either side, it is actually decrease from the equilibrium value. Okay. So this is the variation of magnetic field B. As you can see, this is the maximum value mu 0 I by 2R, and if there are n turns in the coil, then mu 0 Ni by 2R. That is the maximum value at the center. Then on either side of the center, the magnetic field decays. Okay, so this is about variation of the magnetic field created by circular loop. Okay, now we'll see in case of this magnetic field produced by this circular coil, how to find out the direction. How to find out the direction. Okay, how to find out the direction. So I'm showing you here. See, there is a rule. You can see if you have a kind of loop and your current direction of current is in this direction somehow. Okay, this direction. So in this case, if you just hold this coil with your 4 fingers, as you see here, 4 fingers, and tip of the finger should point the direction of the current in the loop, then thumb will show the north pole of the, that will actually give you the north pole, north pole of the magnetic field produced. So in this case, look, this coil, see this figure, you can see, let me give a name A, this is B, and this is C figure. So in this case, you look, the magnetic the current direction of the current is in this direction, anti-clockwise direction. So the north pole will be produced here. Okay, if you apply the thumb rule, this will be applicable here. So north pole will be in the upward direction and south pole will be just in the opposite direction. Okay, that means, you know, when your current is flowing in the clockwise direction, we can just get some idea. Suppose this is a loop, current is flowing in the anti-clockwise direction. Okay, let us not go to that. Clockwise and anti-clockwise. So when the current is flowing in the clockwise direction, and this is anti-clockwise direction, this is anti-clockwise, look this. So in the anti-clockwise direction. So in this case, the magnetic, see, north pole is here. Okay, and south pole will be down. And if you draw the feed lines, it goes like this. Okay. So you can see in this example, the current direction is in the anti-clockwise direction. So upper face of this actually is producing north pole of the magnetic field, and this is south pole of the magnetic field. Now we'll calculate magnetic field due to a circular or any type of arc. Okay, any kind of arc. All right, for any kind of arc. So suppose I have any kind of arc whose ends are making an angle theta at the point where we have to calculate the magnetic field. Suppose I have a curve like this, okay? Then I have to find out magnetic field at some point here, P, say. So I have to add this ends and try to get the angle between them. If it is theta now, then you know the magnetic field can be obtained as theta by 2 pi mu 0 I by 2r. Theta by 2 pi. So it is for, in general, for any arc. We'll apply for semicircle, circle also, and see. Okay, so mu 0 I by 2r. What is this r? R is this kind of radius, okay, radius of the arc, okay, radius of curvature. So mu 0 I by, see here, mu 0 theta by 2 pi mu 0 I by 2r. So if you consider this thing, so mu 0 by 4 pi I by r into theta, mu 0 by 4 pi so mu 0 I by 4 pi r into theta. So that is the formula, mu 0 I by 4 pi r into theta. Okay, so this is the formula as you see here also. I'll just erase this and show you here. Mu 0 by 4 pi I by r into theta. So this is actually the magnetic field due to or at the center of the arc, you can say. We'll apply this very soon. Okay, so we have decided to solve some numerical problem here on the basis of this circular loop, okay, or magnetic field produced by circular loop. So let me write some of the questions. So the first question says a long wire having a semicircular loop. A long wire okay, long wire bent, a long wire having a semicircular, okay, a long wire having a semicircular loop of radius small r. Semicircular loop of radius small r. R and carries a current I, as you see here. So what is the question? question is the magnetic field due to the wire at the point O. Find the magnetic field due to the entire wire at O, due to entire wire. At O, due to the entire wire. So we have to calculate the magnetic field, right? At the point O. So for that, what we need to do? We need to write down the master formula for calculating magnetic field for straight line and the curve part, or for curve actually, or maybe the master formula, or so mu 0 ideal cross r by r cube, or in the form of scalar, we know mu 0 I by I dl r sine theta divided by r cube. So in this case, you look the sine theta. See, for the straight part, suppose magnetic field we want to find out for straight part. So this is ideal is this p cube. Now magnetic field at this point means, see, this is r and this is ideal, and both are having actually direction either this way or just going out for ST. So this also magnetic field will be 0. Okay. So this is 0 because the angle between ideal and this is 0 actually. Ideal and R along the same direction. Along the same direction. Okay. So that's why they are 0. That means, see, here will be the problem. Dl cross R. R dl sine theta. Sine is actually sine theta. Theta is 0 degree. So that's why B is 0 degree. 0. Okay. B is 0. Now we'll see the magnetic field due to the curved path. So magnetic field due to the arc or curved path Q, R, and S. So this is equal to, see, for a for a particular arc, what we have found out expression for mu 0 by 4 pi I by r into theta. So mu 0 by 4 pi I by r, mu 0 by 4 pi I by mu 0 I by r into theta. This is what actually magnetic field. Value of theta as so this theta, this is the angle subtended at the end, okay, by the end. So that will be actually 180 degree or pi. Mu 0 I by 4r. Okay, so for the cart path, you'll get mu 0 I by 4r. Okay, mu 0 I by 4r just by applying previous formula, or you can do it also. Okay, so this is due to the cart path, and the total magnetic field at this point will be only for the cart path, and that is this one. Magnetic field BQRS, that part mu 0 I by 4r. Okay, so we will go to the next part. So this question says, so this figure shows there are two loops having circular segments. You can show question number 2. Two loops. Sorry, two segments. So there are two segments. Okay, I'll not write the whole problem. I'll give you the information. So in this case, you look, there are two circular arc, one of radius r2, another one is of radius r1. See, I have to find out for both the segments, I have to find out magnetic field at the point O. We have to find the magnetic field at the point O. So how do we get that? See here, if I just write the main formula mu 0 I by 4 pi ideal dl cross r by r cube. So in this case, look, dl and r, if they have certain angle, then only you will get some magnetic field. But in this case, see, this is one straight part which is directly in the line of this joining of O and A, so no magnetic field due to this. Okay, so now let us find out the magnetic field due to the arc, suppose of radius r1, this one. Okay, so how do we get that? Mu 0 I, what was the expression we have found out there just for this one? Mu 0 I by 4 pi r. Mu 0 I by 4 pi r. So mu 0 I by 4 pi r mu 0 I by 4 mu 0 I by 4 pi r into pi, the angle, into the angle. So what is the angle this arc is making at this point? This is phi. Okay, mu 0 I by 4 pi, mu 0 I by 4 pi. This angle mu 0 I and angle is here, this part. We have just seen mu 0 I by 4 pi r. That we will just directly use. Mu 0 I by 4 r or 4 pi r. Mu 0 I by 4 r. Mu 0 I by 4 r. Better to use the formula mu 0 I by 4 pi I by r into theta. So bu1 is equal to mu 0 I mu 0 by 4 pi I by r into theta. Mu 0 I by 4 pi into I by r into theta. Okay, actually this is pi, right? So I can write this is pi, is the angle, and this is for 1. For 2 it will be mu 0 I as it is by 4 pi 4 pi r2 into pi. So now we have to find out the direction of this. Direction for this will be upward direction and for this will be downward direction. Okay, so for this it is upward direction and for the other one is downward direction. So we will get mu 0 I by 4 pi, this is common, with the minus sign 1 by r1 minus 1 by r2. So this is the one. Okay, so this is mu 0 I. Okay, so phi is also will be there. Phi also will be there. Mu 0 I alpha, that means sorry, mu 0 I phi is the angle divided by 4 pi, then this one. Okay, so this is the difference actually. Now, so this was actually net magnetic field at that particular point. Okay, suppose I have, suppose I have a coil, sorry, I have a wire bent in this form, okay, like this, and these are of same length, say. So if the current flowing here is 12 ampere, 12 ampere, and semicircle has radius small r, that is small r is equal to 2.0 centimeter. Now we have to find out the magnetic field and its direction. Magnetic field and its direction at the center of the arc. That means here. If this is the center of the arc, look what happens. The magnetic field due to this straight part, okay, this straight part will be obviously 0. Okay. Only thing is the magnetic field due to this curve is in which direction I have to first of all see. So at this point it will be actually going into the plane of the paper just by seeing the, so applying the right hand grip rule. So this is the magnetic field produced by this wire into the plane of the paper, and what will be, okay, now magnetic field due to the straight path, we have seen that that part is 0. As you know, the dl and r vector will be having 0 or pi angle. Now due to this curved path, so this is, say, so due to this curved path, mu 0 I by, see, actually here also we can do mu 0 I by 4 pi, say dl cross r by r cube, okay, or this will be in terms of scalar, mu 0 I by 4 pi dl r sin theta by r cube. So in this case theta will be 90 degree, as you can understand, okay, and say mu 0 I by 4 pi, let it be the previous, okay, first part of this is constant part anyway, dl, so this will be r square then in the down, and this is dl and sin theta. Sin theta is 90 degree, theta is 90 degrees, so sin 90 degrees is 1. So this is actually for db, and if we integrate it to get b, we have to integrate over dl. Dl will actually become pi r here, okay, so pi r. So what you get, you multiply pi r here, so pi and 1 r goes, so mu 0 I by 4 r, mu 0 I by 4 r. This is the magnetic field, and see I have values of current, so b for the curved part will be, so mu is 4 pi into 10 to the power minus 7, current is 12 ampere, and this is centimeter, 4 into 2 into 10 to the power minus 2. Okay, so this will give you, sorry, this is 3, this is 2 pi. Okay, so this is how, if you put the values properly and calculate what you get, will get magnetic field B is equal to, so it will be actually 1.9 10 to the power minus 10 to the power minus 4 Tesla. Okay, so this is Tesla and this is with a minus sign obviously. And see, this is the case and this is into the plane of the paper. The same thing is repeated in another way. So if this is actually turn, then also magnetic field due to this part will be 0 and this straight part will be 0, and magnetic field will be only for this curved surface. Sorry, this is magnetic field. B we have to calculate for the curved part. Here also mu 0 I by 4, mu 0 I by 4R. And put the value, you will get actually same value. Okay, I'm sorry, this is 10 sorry, 1.9 into 10 to the power 1.9 into 10 to the power 4 Tesla. Okay, so we can actually see the direction of this magnetic field here. This will be actually down upward. But the direction will be in this case coming out. Okay, so here the direction will be okay, so it will be going all right. So this is how we have to, oh I'm sorry, this is actually, that's why the direction was having certain problem. The direction of the current is not this way, that's why direction will be different. Okay, this is the direction. Now it will be upward. Okay, so coming upward, coming out of the phase, whereas the value will be the same, 1.9 10 to the power minus 4 Tesla. Okay, so with this we will stop it here for today. Next day we'll discuss about magnetic forces, etc. Or no, before that we'll discuss solenoid, toroid and related concepts. Okay, so thank you for your patience. Bye for today.